So let me just start, before I forget, with some acknowledgements. I've worked with many people over the years, in particular various experimentalists. I'll be showing you STM images from the groups of Christoph Renner, James Owen, who I did my PhD with and have collaborated with ever since, and then in Japan, Kazushi Miki and Keisuke Sagisaka. In theory, Mike Gillen, who's here, gave me my first job. So I'm profoundly grateful to him for that, and he has guided me through my career ever since. Tsuyoshi Miyazaki and I have worked together since about 1999, and it's turned into one of the most productive partnerships of my career. And more recently, I've had the pleasure of visiting Bordeaux, which of course does good science, but also does good food and good wine. And there are various funding agencies. I would also like to acknowledge my family for their patience and love and support with me over the years. There are, of course, various students, postdocs, and master students, at least some of whom are here today. I'm not going to go through them, but again, I am very, very grateful to all of you for all of the work and the support that you've done with me, without which I wouldn't have managed it. So everything I'm going to be telling you is to do with computational physics. This is what I do. I am a computational physicist, and computation is actually emerging, probably now I think, as the third leg of the stool of physics. So you have experiment and you have theory, and computation is there in between the two, providing stability and balance. It allows you to interpret experiment and predict results. It allows you to do more than you could do with theory on its own. And it works over all different areas and length scales of physics. So you can go down to the very, very tiny, so quantum chromodynamics, where they've even actually designed an entire supercomputer purely to do QCD calculations. There's my area of electronic structure. There's atomistics and coarse graining, finite element modeling. I was briefly involved in finite element modeling of transistors on gallium arsenide. Up to fluid dynamics, we've recently been hearing a lot about climate dynamics and planetary dynamics, and of course you then go on to galactic dynamics. So you cross many, many orders of magnitude. And I will also very briefly talk on the fact that computational physics is extremely useful for teaching. It allows students to get a much better grasp of the basic physics and to do experiments themselves. And I think this is just starting to open up. This is the very beginning of a new era. I'm going to be talking about atomistic simulations, so that sets the length scale. We define a simulation cell. Okay, it's a box, and that represents our system. And those boxes contain anywhere from 2 to maybe 2 billion atoms. That's about the rough order of magnitude over which you actually count atoms. And at the bottom here we have a standard crystalline silicon cell. On the right we have F1 ATPase, which I actually got from my brother because he did his PhD studying that with John Walker in Cambridge and crystallized that protein. This is a ribbon structure, so that's not actually showing you all of the atoms. There are at least 20,000, 30,000 atoms in that structure. Now, let's just stop and think a little bit about how many atoms that means. If you wanted to take, let's say, a mole of carbon, that would be 12 grams of carbon. That would be 6 by 10 to the 23. We all know Avogadro's number. Let's round it up to 1 by 10 to the 24. That's 10 to the 8 atoms on each side of a cube. Okay? So in order to do even 12 grams of carbon, you would need an incalculable number of atoms. If we took 1 million atoms, for the sake of argument, I will be showing you some million atom calculations later, then you would have a cube with 100 atoms on each side. Okay, but that's still only a few tens of nanometers. That's not a very large amount of material. So we are often faced with a difficulty in trying to work out what we're modeling and how we're modeling it. And I'll be showing you some of those problems later. And the fundamental thing we do in an atomistic calculation is we start with some positions, and from that we calculate an energy. Okay? So just to illustrate this, we start up here with the energy, and from the energy we can get many, many different things. We can get a cohesive energy, tell us how strongly bound a crystal is. Though once you start to move away from the realms of physics and into material science, you realize that actually the strength of materials doesn't depend so much on the individual atomic positions as on the microstructure, which is important to study. Using energies, you can calculate elastic constants. What's the behavior of a material when you stretch it or bend it? You can calculate forces in almost all atomistic simulations. A force is just a change of energy and a change of position. From forces, you can calculate stable structures. You can get dynamics, which then give you free energies, and thermodynamics, and many useful things. And I'll also be talking about what's down here, the electronic structure. This is something that is very, very important and allows you to understand more about the bonding and the properties of materials, their responses to experimental probes. Returning again to the question, how many atoms do we do? Not long after I started working with Mike Gillen in Kiel, he did some calculations with Dario Alfei, who's also here at UCL, on iron at the Earth's core, and received a phone call from a journalist who said, I understand that you've done some calculations on the atomic structure of the Earth's core. Mike said, yes. And then the journalist said, so how many atoms are in the Earth's core? Now, at which point you have to have a slight readjustment, because actually their calculations had used 64 atoms. Okay? It's not quite as many as you have in the core. So you have this internal problem of efficiency versus accuracy. And typically, efficiency implies few atoms, and accuracy implies many atoms. That's what I would argue, because real calculations, real systems, must take into account the defect structure, the surfaces, and that needs a large system. With a few atoms, you start with a simple representation of the system. With many atoms, you come to a more realistic idea. And then moving down to the bottom of the screen, I've given some examples. So alloys or doping really does require a great ability to shift from one end to the other. If you want to do a really dilute alloy, then you're going to need to move to the very, very many atoms. So if you want 1 in 10,000, 1 in 50,000, which is the typical doping levels of a semiconductor, then you need to be able to model 50,000 atoms and the electronic structure of those atoms. Obviously, with perfect crystals, you can get away with very, very small cells, and that's how we started back in the 80s. That's what solid-state physicists have been doing for a long time. And then as you get to larger systems, you can model defects and dislocations and the kind of problem where things are very large. Atoms interact with each other, and that's what gives us interesting physics. It's a little bit dangerous, given that I've got colleagues in AMOP, in atomic and molecular physics, to say that atoms aren't interesting on their own, but I would say that most of the interesting physics comes when atoms start to interact with each other. And those interactions involve electrons. So bonding involves electrons, but actually what's also more important these days is non-bonding interactions, which also involve electrons. You can fit atomic interactions to simple patterns. So there's a little sort of picture up here of a Leonard-Jones type potential, which you can calculate with 1 over r to the 12 and 1 over r to the 6. You just add those two together. But actually, if you want to get real accuracy, real predictive power, you need quantum mechanics. So we're going to think about quantum mechanics. The force fields is the generic term for these types of approaches where you replace the interaction between atoms with springs. They are enormously successful. They're widely used, particularly in biochemistry, but in other areas as well. And there are two main quantum mechanical methods, one of which comes from the chemistry community, the quantum chemistry approach, post-Hartree-Fock, one of which is density functional theory. These days they're starting to mix into each other, meld and overlap, and you're seeing people put bits of quantum chemistry into density functional theory. And they both give you the electronic structure of a system. I would say DFT scales better with size. You can go to larger systems with DFT. And I'm going to be talking about density functional theory calculations. So what do we do? Well, ultimately, we need to solve the Schrödinger equation. And in my quantum mechanics lectures, it's one of the things that you can point out as being really, really simple and beautiful and trivial to write down, but an absolute nightmare to solve. In fact, it's impossible to solve for anything more than hydrogen. Okay? You can't go beyond that. Possibly, you could argue you could solve it for helium plus if you wanted to be really pernickety. And the problem here is that you have a many-body problem. So really, you have to take into account the wave function of all of the electrons and all of the nuclei. However, nuclei are much more massive than electrons, so we can apply a series of approximations and first of all say that they're slow-moving, so we can effectively ignore them, and also we can say that they're classical, so we can remove their wave functions. We don't have to worry about their quantum behavior. This is, of course, not always true, and there are a number of extremely interesting bits of science where you have to consider the quantum nature of nuclei. But even when we've removed the nuclei, the electrons are still a problem. There's still a many-body problem. I'm not going to talk really in detail about how we solve this because I don't have time, but just to give you an idea of what happens in density functional theory, it's now become widely used in all these different areas. In physics, chemistry, earth sciences, material science, biochemistry. You find people doing DFT in engineering departments. It's spread throughout most of science. And the simple change we make is here. The energy becomes a functional of the charge density. So we throw away all of the many-body interactions, we stop worrying about all of the different electron bands, we just worry about the charge density. And that simplifies things immensely. And you can show that you rework the many electron problem into non-interacting electrons in an effective potential. We push everything into one problem, one area. And we can approach what the chemists have as a goal, which is chemical accuracy, the kind of thing that will enable you to predict chemical reactions with confidence and accuracy. And just to show you a little bit more about that, what we're doing is we're making what is fundamentally an exact transformation. So the Nobel laureate Walter Kohn, who died recently, showed that you could do this reformulation without losing any accuracy. The problem is that you put everything into this potential here, the effective potential, and we don't know that. It's quite likely, I think, that we will never know that. We will never be able to write down the effective potential. So, of course, we then do what all physicists do and approximate. And we make a series of approximations. In the original papers, Walter Kohn actually used the local density approximation, which came out of fluid theory, so classical fluids and water flow, and that became a pillar of DFT and electronic structure into the early 90s. People then decided that just using the density on its own maybe wasn't good enough and brought in gradients. And since then, we've added more and more complications. We now have gradients, we have curvatures, we have exact exchange, we bring in all sorts of other things. So this effective potential, the Kohn-Sham potential, is where all of the hiding, the approximation, and the sophistication lie. I'm not going to tell you any more about DFT for now, because I'm going to go on to the key area I want to talk about, which is modeling and interacting with STM. So down at the bottom here, we have a picture of a typical STM system. It's in steel. In fact, if you look into the basement of the LCN, you can see a number of these down in the very basement. They're steel because you can bake it, okay, which means that you actually heat those things up to 150, 200 degrees, leave it over a weekend, drives all of the absorbed gases off the inside, and then the vacuum inside the chamber, which you need to do STM, is extremely hard. So in the interior of this, you have this little thing here, this STM controller. It's about 10 centimeters long, and what you have is you have a sample down at the bottom here, and then a tiny little tip just here. That tip is held maybe 1 nanometer, a billionth of a meter above the surface, and a current is applied between the tip and the surface. Now, because it's a quantum mechanical system, because the distances are small enough, even though there is no electrical connection between the tip and the surface, a current flows. Because it's quantum mechanical, it's exquisitely sensitive to the distance between the tip and the sample. So the distance varies exponentially, you get exceptionally good resolution, and by measuring the current as you move this tip around the surface, you can get a readout of, naively you would think, the height of the surface. Unfortunately, it's more complicated than that. It's not just the height, it's the height and the electronic structure. So you have to interpret, you have to think, you have to dig around. But that's what an STM looks like. That's roughly where we're working. At the beginning of my PhD, I actually started doing experiments. After 3 months, it rapidly became clear that while I could do them, it wasn't really a good plan. I moved into theory, but I found people to work with. And that turned into an enormously useful and productive relationship. And it's something I want to encourage and emphasize, is that working with experiment is absolutely vital. So when you work with experiment, what's going on? What do you actually have to do? Well, the experimental group have to prepare the surface. And that on its own is not trivial. It involves, with silicon, it involves hydrogen fluoride, one of the nastiest acids known to man. You have to prepare a tip, which involves cutting and then annealing a very small piece of tungsten. You have to deposit something on the surface quite often if you want to do anything interesting. Figuring out how to get the particular atom you want at the densities you want is very difficult. Once you've created a surface and potentially deposited material, you have to treat it. Maybe you have to anneal it to make it flat. Often you will add hydrogen, or you'll remove hydrogen with an STM tip. And once you've finally done that, then you start the imaging process. And the imaging process itself is enormously difficult. If any of you students here have any interest in working with experiment, I would encourage you to spend time actually in an STM lab or whatever the lab is, because you learn so much about what you can and can't do that it is enormously valuable. Now, if you're, like me, a modeler who can avoid the nastiness of hydrogen fluoride, the explosiveness of disilane, the poison of arsenic, the carcinogen of trimethyl gallium, put them all into a computer and back off from the dangers of experiment, you build a plausible structure. Okay, now that sounds simple, but it's not, and I will show you a number of the iterations we've gone through one particular system. Once you've done that, you relax the system and you model the experimental data. You go back to the experimentalists, you make comparisons, they tell you that you're talking rubbish, you refine your model, and everything continues. And it goes round and round and round. So long as you both understand what you're doing, the limitations, the questions, and the difficulties, it works very well. I have encountered both experimentalists and theorists who've had no time and no patience at all with the other discipline and have simply told someone, oh, you're not doing your experiment carefully enough, or your modeling is wrong. Now that just doesn't work. You have to build bridges, you have to talk and think. I wanted to put up an overview of some of the areas that I've worked in. So most recently I've been working in UCL with colleagues on dopants in the silicon 001 surface and the 111 surface. I've done some work on ammonia on silicon. I've worked at Geneva, work with manganese on silicon, and also on titanium diselenide. In all of these images, you're seeing comparison between modeling and experiment. So for instance, this manganese wire, I find this enormously annoying because the agreement between the experiment and the theory is actually pretty good, but I don't believe the theoretical structure we've put in to get that agreement. I think there's something missing. The titanium diselenide, I'm actually really pleased with. That actually agrees extremely well. That's become a very fruitful area. The dopants, again, you can see that we're getting very, very good agreement between experiment and theory. There's other areas I've worked in, so silicon 111, germanium growth, hydrogen on silicon, and the silicon 001 growth. What I really want to talk about today is this, the nanolines you get when you put bismuth down on silicon. So I want to tell this as a little story, excuse me, of the dangers and the interests and the trials and tribulations, both of experimental STM and of modeling. So this is what my colleague James Owen saw one morning on coming into the lab. Now bismuth is a surfactant, which means that you put it down on the surface of a growing semiconductor to flatten things. Okay, so if you're wanting to grow, say, silicon or germanium on silicon, putting a layer of bismuth down first improves the quality of the growth. It makes the terraces wider, it removes hills and valleys, and it generally improves things. And James was involved in a collaboration with Japan, and they were simply looking at the surfactant effects. Now, what the postdoc who was in Oxford at the time had done was left a bismuth-covered surface annealing at about 600 degrees overnight in order to remove the bismuth, because he wanted to start again. He wanted to get rid of it in a gentle way without destroying the surface. So he left a note on the whiteboard to the students saying, flash the sample, in other words, blow the top layers off, and then and then we'll start again. James turned on the STM instead of flashing and saw this. Now, let me go to another picture. Sorry, I was going to talk about silicon first. Excuse me, my mouth's gone dry. I will tell you a little bit more about the bismuth lines when I first introduce you to clean silicon, because you need to know about clean silicon to understand that. This is an STM image from a colleague called Tetsuya Narishima, who's in Japan. It's a beautiful image of silicon 001. I hope you can see that there are lines down here. Okay, those are rows of silicon diamonds. That's pairs of silicon atoms. When you get to a step edge, the row direction goes through 90 degrees. And at the step edges, you can probably see that there's some kind of zigzag effect. That's because those pairs of silicon atoms aren't actually flat. They tilt. And they alternate along the dimer row. In the middle of the terrace, because this is a room temperature picture, they're oscillating backwards and forwards. So you see an average. At the step edges, they are pinned. It's a very reactive surface which you can passivate with atomic hydrogen, and you'll be seeing some results passivated with atomic hydrogen later. It's extremely technologically important because it's the surface that all of the silicon chips, all devices are made on. Just to show you, this is my view of a silicon surface. Again, you can see that you've got dimer rows going up and down, so you can see a dimer here. And just to show that to you in perspective, you can see here the dimer rows going up the picture, and you see that they're oscillating. They're flipping backwards and forwards. So let's come back to the bismuth lines. you see the scale bar at the bottom here. That's 100 nanometers. So these things are hundreds upon hundreds of nanometers long. You can grow them a micron or 2 microns long. And given that they are 1 nanometer wide, that gives them an aspect ratio of 1,000 to 1. And they are actually completely perfect. There is never a kink. I think in some ways they're the most straight structure there is. So this is what we had as an image. You can see a zoom in here. And our initial thoughts were that you had an area here of 3 silicon atoms, 3 silicon dimers replaced by 2 bismuth. And so we came up with, they did some modeling, some imaging rather, at different voltages. So here we have a high voltage and then lower voltages progressively. So as you get closer to the Fermi level, you see that the bismuth lines become dark. And the model that we came up with was this. So it is simply where we've taken out 3 silicon dimers, so there would have been a silicon dimer here, 1 there, and 1 there, and we put in 2 bismuth dimers. It matched what we could see in STM. It seemed to be relatively stable, but there was no reason for the lines to form. There was no straightness. There was nothing forcing things to be straight. But at the time, we had no more information. Now, as is the way with science, you stop and you look and think what's going on. So here's an overview of what we could see. So these images here show you a bismuth-covered surface, and you can just see here bismuth lines starting to form, buried in the surface. They are perfectly straight. They're 1 to 1.5 nanometers wide, and they never kink. They never change a corner. There's nothing there. So there's something really, really forcing this straightness. Here's another image, larger scale, showing you that they will grow into step edges. So they will actually tunnel into a terrace. They will grow out over another terrace. They will grow little promontories. They're enormously hard to stop. The only thing that will stop them is another nanoline. They don't form immediately. If you take a bismuth-covered surface, it's at least 5 or 10 minutes of heating at about 550, 600 degrees C before they start to form. So there's a high energy barrier to start. Once they start, they grow like mad. They go incredibly fast. Now, a rival group in Japan then published an image here. It's not terribly good quality because I'm afraid that the printing that you can get these days is not very good. The PDFs aren't very clear. What we could see, though, down here is that actually it wasn't taking up the space of 3 silicon dimers. It was taking up the space of 4. And that sounds like a rather small difference, but it was an enormously important change because it shifts the registry. It changes the relationship between the lines and the substrate. And they proposed this structure down here. So you can see that what they've done is they've taken out 1, 2, 3, 4 silicon dimers and replaced them with bismuth here and here. That's no good because the bismuth dimers are too close. They're far too close. So then began a sort of a 1.5-year long hunt. If you know the poem, The Hunting of the Snark, it's very much like that. It felt like an enormously fruitless search going round and round and backwards and forwards. We came up with many, many different possibilities, and then James managed to find a way to look at the surface with atomic resolution. He found a way to put hydrogen down and passivate the surface. So you can see all of these little dots on the background are individual hydrogen atoms on the top of the silicon dimers. And what we could see there was that not only do they take up the space of 4 dimers, so our rivals were right, but the bismuth lie in between the silicon dimers, and that's an enormously important point. So here are some of the different structures that we came up with. I mean, we tried everything we could think of. And what happened here was I actually gave my modeling program to the experimentalist, and it was a tight-binding program, so it was very fast. It would run very quickly. It was at the time when Mac was bringing out nice MacBook Pros, so in his idle moments, which of course experimentalists have all the time and theorists never do, he would sit and construct a structure and relax it and try another one and try another one and try another one. And we went through all sorts of different possibilities until, again, another piece of serendipity. So the discovery of these lines in the first place was an accident. And then one day I was going to the PRB website just to pick out a paper, and they have these pictures of papers that have just been published, and there was a picture there of arsenic on the germanium surface. And at the arsenic step edge, at the germanium step edges, they could see in STM a reconstruction. And we saw that and suddenly thought we could use that. And we turned that into this model, which we now believe is the bismuth line structure. We call it the Haiku model because we discovered it in Japan, and there's the Japanese verse form, the Haiku, which is 5 syllables, then 7 syllables, then 5 syllables. And if you look at this, you can see that in here you have a ring with 5 neighbors, and then you have a 7-membered ring, and then a 5-membered ring, and then a 7, and then a 5. It's completely reconstructing the subsurface. So down here you can see the standard silicon structure, hexagons of silicon atoms. In here you've got all sorts of reconstructions. You also actually have a little bit of wurtzite structure in there, which is completely changing around the stacking of silicon layers. If you do any work with nanotubes, carbon nanotubes, these structures might actually look familiar, because the 575 defect structures in carbon nanotubes are very familiar. You get them by rotating a pair of atoms in a carbon ring. The registry and the appearance match the STM. When you do a total energy calculation, it's an extremely stable structure. So we believe that these were the structures. Here's a perspective view, and again you can see that this whole part of the silicon surface has been completely changed and reconstructed. It's gone down 5 layers below the surface. That's a nanometer and a half. There are very few structures I've seen in my work on silicon where you go that deep. It's very, very unusual. But it does explain why they won't kink. Because if you try and take this core and move it just one lattice constant to the right or the left, bonds break, everything goes, and there's a huge high energy problem. And then just to emphasize this, you can see that here you actually have 1, 1, 1 planes, and within that you've changed the structure of the substrate. There was no more experimental evidence we could get to back this up at this point. We had no way of knowing if this was right or not. It looked good, the energy was good, all of the predictions were good. And then they discovered in Geneva that if you put a high flux of hydrogen down, you strip the bismuth off the surface. It was a complete accident again. So here on the left you see the starting structure, that's the surface, there's the bismuth line going down the middle, here are the silicon dimeros. On the right you have what happens after you treat with a very high flux of atomic hydrogen. So you can see that the dimeros here now have a very double dot appearance. That's because you've got hydrogens on each side. And you're left with this extraordinary trench in the middle. There's XPS data down at the bottom that shows that the bismuth is removed by the hydrogen. And there is no way to explain this trench without this Haiku model. And if you do an STM simulation, which I've put in here, you find that they match almost exactly. When I gave a slightly different version of this to my colleague Veronica, who I wrote a book with, as an illustration, she actually had to change the color scheme for the modeling, the model STM image to make it clear. Because when it was reproduced on the page, if you didn't change the color scheme, you couldn't actually see the difference between the experiment and the theory. So we are now very, very confident that this is what's happened. We still don't know why they form. We still don't know how they grow. We don't know the nucleation process. This hydrogen-terminated surface is air-stable. Now, to a UHV STM surface scientist, that's enormously valuable because it means that you can actually take them out, move them between characterization tools, maybe even transfer between places. I've said they're stable. If you're careful, then the lines are inert to hydrogen or oxygen, so you can actually mask the surface, you can oxidize the surface, which allows you to do a variety of treatments. The growth mechanism is unknown, and I'm not going to go into it now because I want to talk about other things, but I can tell you more later. You can overgrow them. We want to functionalize them because they're not conducting. This is an STM image of what happens if you put silver down on a bismuth line surface. You can see that you get silver islands on top of the bismuth lines. Unfortunately, you also get silver on the background. So it's not 100%. This just shows you can analyze those islands. Indium is more interesting because it really doesn't go onto the background very much, and it does sit on the bismuth lines, and you get different things. So you get little things here which are zigzaggy, and things here which are like hexagonal islands. Let me show you that in more detail. You can see here are the hexagons, and here is a zigzag. And that zigzag actually turns out to be a one-dimensional 3-5 structure. So it's indium bismuth, indium bismuth. It's a 3-5 in 1D, which I think you can also make in the interior of a nanotube, but you can't make anywhere else. We haven't found any uses for that, but it's certainly interesting, and it would be good to try and characterize that further. You can bury the nanolines. Normally, because bismuth is a surfactant, if you grew more silicon on top, the bismuth in the nanolines would float. If you put down an extra layer of bismuth, if you cap with bismuth, then you can bury them. And you retain the periodicity, and we're still working on understanding what goes on with this. So that was the bismuth nanolines. I wanted to show you one more experimental picture because I'm particularly proud of this. This is what happened when my colleague Keisuke Sagisaka in Japan put phosphorus down on the silicon surface. So he took an indium phosphide sample and he heated it, and that emits P2 or P4 molecules, so just pairs of phosphorus, 4 phosphorus atoms. And he got all of these orange STM images and sent them to me and said, what do you think? So I started with just single phosphorus atoms on the surface and got absolutely nowhere. So I put them down as pairs of phosphorus atoms and got what you can see here in grey. And you get a wonderful, wonderful agreement. So as you go down the column, what you're seeing is the changing STM bias, the changing voltage on the STM tip. The top 2 rows are negative, so that's when you're taking electrons out of the sample and putting them into the tip. The bottom 2 are positive bias, so you're pushing electrons from the tip into the surface. And you can see, if you look carefully, that actually the shapes, even down here, this particular pair is rather unusual. You've got some very odd shapes. The theory and the modeling, the theory and the experiment match beautifully. It takes time, and it takes a lot of patience, and it takes work to understand what the other person is doing. And for me, that's actually the key, is to spend time with experimentalists, to listen, to learn. And when you do that, you can actually produce good results. So having talked about my experimental collaborations, I now want to sort of change gear and talk about the other part of my career, the other part of my work, which is modeling and developing DFT codes. So there's a huge amount of work going on in the world at the moment extending DFT because it is so widely used. There are people who are trying to extend accuracy, so they're creating more and more of these functionals, fitting them to more and more material properties. They extend functionality, so they enable us to calculate NMR spectra, this kind of thing. But what I'm going to talk about is down here, extending the size that we can address. So traditional DFT codes scale with the cube of the number of atoms in the system. So that's up here, and the CPU time goes with n cubed. The reason that happens is a little bit complicated. I can explain to you later if you're interested. What it means is if you want to double your system size, it takes you 8 times as long. If you want your system size to be 10 times as large, it takes 1,000 times as long. And if you're given a computer by the government that's 1,000 times bigger, you can only actually do 10 times as many atoms, which maybe isn't quite what the accountants want to hear. But that's not actually what we would expect. We should expect DFT, electronic structure calculation, to scale linearly with the size of the system. Okay, so we double the system size, it takes twice as long. 10 times the system size, 10 times as long. Give me a computer 1,000 times bigger, and I can do 1,000 times as many atoms. And you can show the electronic structure, so bonding and the orbitals that you get in atoms and in molecules and in solids, is localized. So this is an image here of what's called a Vanier function in silicon. It's one of the orbitals that you can calculate in silicon. And you can see that it's very local in space. It's confined to a specific area. Now, if all of the electronic structure is confined to one area, then I can take a chunk of silicon here, add on another chunk here, and I won't affect this. So therefore, the effort required to model this bit is independent of the effort required to model this bit, and the scaling ought to be linear. There's another reason why we want to be able to use linear scaling, Petascale Computing. So down at the bottom here we have a picture of the K computer in Japan. It has its own subway stop in the city of Kyoto, of Kobe. And it has this, this character here, so this is done in beautiful calligraphy, but the more sort of standard typography is here. In Japan you count in factors of 10 to the 4, not thousands like you do in the West. And this character represents 10 to the 16, which is 10,000 million million. And it's pronounced as K, and that's actually the power of the computer. It can do 10 petaflops, or 10,000 million floating point operations every second. But to be able to use a machine that powerful, with that many cores. So they do it by having over 700,000 cores. The new Chinese supercomputer Tianhe 2, I think, has maybe over 1 million cores. It certainly has more power than the Japanese. It's now up about 20 or 30 petaflops. To be able to use that, you need to change the way that we do DFT, because standard DFT codes don't scale well with system size, certainly once you get beyond a few thousand cores. And it won't surprise you to learn that the kinds of things you do to make DFT scale linearly also work very well on large computers. So normal DFT codes have a limit of about 1,000 atoms. You can go a bit beyond that. You will find some calculations when they've gone to 5,000, possibly 10,000 if they had access to an entire machine. But typically we stop at around about 1,000. And that's because of this n-cubed scaling. And the CONQUEST code, which has been developed by UCL and NIMS, scales linearly with system size. And we've gone to over 2 million atoms. So we've gone a whole 3 orders of magnitude beyond that. And I'm going to show you a little bit about that in the next few minutes. So how do we do this? How do we make DFT local? Well, we go back to the roots of DFT. So the standard DFT codes, I showed you the Schrödinger equation when I was talking about the potential, the Cohen-Shum potential that we don't know. They actually solve for the wave functions. Now, they're not the wave functions of the system, but they're still a wave function. What we do with CONQUEST is we define instead a density matrix. So that just tells us about the density of electrons between 2 points in space. You can show that this decays with distance. So as 2 points in space become further and further apart, the coherence between them, the electronic coherence between them, decays to 0. And if that's the case, then you can impose locality. You can say, right, once we've gone beyond a certain distance, I'm just going to truncate it. I'm going to set everything to 0. I'm going to stop having any coherence. And that will then mean, of course, that your electronic structure is local and the scaling is linear with system size. This is a very well-controlled approximation. So you can increase the size that you are, the truncation size that you're applying on the system, and the energy will converge variationally to the ground state energy, the full unrestricted energy of the system. Now, what we do is we actually reformulate this, so we work in terms of a separable density matrix. The thing to note here is that we have functions that are local in space. So these phi I alphas are centered on atoms. And then we have a matrix k I alpha j beta, which joins them. So these functions phi I alpha are restricted to be within a sphere. So once you go outside that sphere, then they go to 0. And this density matrix Kij is set to 0 when 2 atoms are more than a certain distance apart. So here's a little bit of detail on CONQUEST. It's world leading in terms of order n codes. I've not yet seen another code that's gone beyond what we've done. So we've done over 2 million atoms. And on the K computer, we've gone up to nearly 200,000 cores. That's 25% of the machine with perfect scaling. So there's been no loss in efficiency as we've gone to that. We've put in molecular dynamics, and we've only gone to 32,000 atoms for that because we just didn't want to go too far. And we've demonstrated real order n applications. I should point out there are other linear scaling codes out there, notably OneTep, which comes out of Cambridge, and Imperial. Siesta, the Spanish code. You notice the difference in naming techniques between the UK and the Spanish codes, and various other codes that come from Europe and Japan. So in order to find our ground state, to minimize the total energy, to calculate that, we vary the support functions and the density matrix. We, of course, have to impose an electron number. That's just saying that we've got a finite system that we've put a finite number of electrons into. The standard problem for those who do electronic structure is self-consistency between the potential and the charge density. And idempotency just means that electrons are fermions. You can only have one electron in each state. We impose locality, we force the support functions to stay within a sphere, and we truncate the density matrix. I'm not going to talk about these because they're rather technical. I will just mention that there are 2 approaches at the moment to truncation. So one of them is spatial truncation. In other words, when 2 atoms are more than a certain distance apart, I set the density matrix to 0. To characterize things a little bit, to caricature things a little bit, that comes out of physics. Okay? It's a variational approach. It's well controlled. As you increase the distance, you guarantee that the energy goes down. Technically, it means that the matrices have a consistent sparsity pattern. They have a consistent pattern of non-zero elements, which makes parallelization much, much easier. Coming from the other direction, again to caricature from the chemistry community, you have numerical truncation. Now, with numerical truncation, you say once an element has reached a certain size, once it's below a certain size, we set it to 0. That has advantages. It means that you'll have a much better idea of how you're approximating, how you're truncating your density matrix, but it does mean that it's non-variational, and it means that your sparsity patterns vary. So the parallelization is much, much harder. And it's interesting to me that most of the numerical truncation codes only go to a few tens of cores, where most of the spatial truncation codes go to many, many cores. I'm not going to talk about the support functions. This is a plot that I made for Mike Gillen's first retirement symposium. We've done 2 now, I think. This was about 10 years ago, wasn't it, Mike? Yeah, so this was where we were celebrating Mike's 65th birthday, which nominally means you retire. 10 years later, we've just had another workshop to celebrate Mike actually retiring, honestly. But this is where we actually wanted to, I wanted to see how far we could go. So we use bulk silicon, which is our favorite system because it's very, very easy to understand. It's very easy to make large unit cells. And once you're dealing with cells which have 1 million atoms in them or 2 million atoms in them, those are 130 megabytes in size. So just creating them, moving them from machine to machine is non-trivial. And then this plot here just shows you the increase in time against the increase in size. But it's a plot where we had to use logs in order to fit all of the data into a comprehensible size of the plot. And we've gone from 512 atoms down here to over 1 million atoms up here. And you see that the time increases linearly with the number of atoms, and the energy increases linearly with the number of atoms, as you would expect. Now, my colleague Tsuyoshi, when he had access to the K computer, also wanted to push this and see exactly what he could do with that. So he's done the same thing, but in a subtly different way. So here he's showing the total wall time per CPU. So per chip in the computer, this is the total time. And the way that CONQUEST works so efficiently is that we fix the number of atoms per chip. So we say 50 atoms per chip, and then if you want to do 50,000 atoms, you need 1,000 chips. And what you hope is that as you increase the number of atoms, the number of chips, the total time per chip stays constant. And you can see that all of these lines here are flat. So not only do we scale to 1 million atoms, as he has noted in a rather excited font, we also scale up to 24,000 CPUs, and there are 8 cores per CPU. So that's the 200,000 CPU, 200,000 core scaling. And we see no reason why we couldn't go on. Given that Japan counts in factors of 10 to the 4, the obvious thing to do next is 2 sots of 10 to the 4, which is 10 to the 8, which is oku in Japanese. But I think that in the UK, oku atom man doesn't sound quite as good as million atom man. We're also working hard on accuracy in CONQUEST. We're wanting to make sure that not only can we go to large systems, but we can treat them accurately. Exchange, this is an important development within DFT. It adds a great deal more accuracy, and we are putting that into CONQUEST. We've shown that we can do that linear scaling. Time-dependent DFT allows you to calculate excitation spectrums, and down here you can see the excitation spectrum of benzene, and you can see that actually the first peak is modeled extremely well, and the general shape of the red line, which is experimental, and the black line, which is CONQUEST, agree very well. I will be the first to admit that 12 atoms of benzene is not the same as 1 million atoms, but we can scale this up, and this plot here shows you that as you increase the number of atoms doing the same kind of calculation, the time increases linearly. So we can do all of this with linear scaling. We've recently done some molecular dynamics, that's moving atoms around, which gives you access to thermodynamics and all sorts of important quantities, but I won't talk about that now. We have done some work on biological systems, though we're still very much dipping our toe in the water here. An ion channel, I just want to show you this briefly. So you see this sort of pale blue spiral in the middle of the figure here. That is an ion channel called gramocidin A. And if you add up all of the atoms just in that spiral, which is the channel itself, you get about 600, okay, which seems like a reasonable number of atoms to model. If you then add in the cell membrane and the water, top and bottom, then you get 17,000 atoms. So in order to model a 600 atom ion channel in a biologically realistic system, you need to go from 600 to 17,000. Now, typically people will do this kind of calculation with a force field. So that's where you replace the atomic interactions with springs. But when you're thinking about ions, that becomes very, very challenging because ions are charged and so they polarize the atoms, the environment around them. And ion channels are fascinating. So this grammacidin A will let monovalent ions, so that's singly charged ions like sodium, pass through. But divalent ions like calcium, calcium 2+, do not go through. And we don't know why. You couldn't answer that question with a force field, and we're looking at answering that with CONQUEST. We haven't done it. What we have done is we've looked at the potential in the channel, and we've shown, at least so far, that the side groups, the details of the protein, don't change the potential in the channel. That was one thing that had been advanced as a suggestion. We need to do more, and we need to find the right biological questions to answer. This is more my area of expertise. Solid state semiconductor surfaces. In fact, this image down here on the left was taken by my colleague Ian Goldfarb while I was in Oxford doing my PhD. When you put germanium on silicon, there's a lattice mismatch. There's a strain because the lattices are about 4% different. To start with, they go down flat with just little missing rows of atoms. But suddenly, when you get to about 3 layers of germanium, this happens. You start to see what look like houses from above. And this is a slightly higher resolution STM image in the middle taken from above and then rendered in 3D. And these are kind of the canonical set of what are called 3D growth when you look at strained semiconductors. And there's some good experimental evidence that these faces here, so this kind of triangular face, not only that this face here will grow outwards, and John Venables, in fact, did some of this work, so that this hut would elongate in this direction, but also they grow from the top down. In other words, the growth starts up here and then spreads down. And again, there's no real understanding of why. So what have we done with this? Well, we started by asking, can we actually do realistic calculations on these systems? And the answer is yes. So we wanted to check that we could actually find the ground state, and we can. And then we wanted to check that we could actually relax the structure of the hut. Because it's kind of a large system, there's an awful lot of strain you have to worry about. And that worked. This is the biggest system we've done so far. So you can see that this is rather a large hut cluster for us. It's 200,000 atoms. We used 1% of the K computer. So that does suggest that we could certainly get to relaxations of tens of millions of atoms if we had access to the whole machine. We've also done some calculations on how they might grow, and we did that by simply taking germanium dimers, pairs of germaniums, and putting them down on the end surfaces and on the side surfaces in different positions and calculating the energy. I don't have time to go into it, but what we can do is we can show that indeed they do nucleate at the top of the facet and then grow downwards like this. Whoops, that was exciting. That's the one I want. They then do grow downwards in the way that is seen experimentally. I'm going to have to move back to my computer here. We are using CONQUEST to look at semiconductor nanowires. So there's a large amount of work we're doing on core shell nanowires. So a core shell nanowire is where you start with a nanowire with germanium or silicon, and then you grow a shell of the other material. And they're very interesting experimentally because they will confine electrons either to the core or to the shell. So if you can dope one area, then the electrons will be in the other area, and you get extremely good transport properties. In the last couple of minutes, I just want to make a few sort of more broad statements, things that have occurred to me during my career. So I've been talking about bridge building and experiment and theory. It really is a different culture. It does take a long time to understand what experiment can do if you're a theorist, or what theory can do if you're an experimentalist. And it takes effort and openness. And I've not always managed to make that level of connection that I have in a few places. Other areas that you see this idea of bridge building, so teaching. It's really lovely to see a number of people who've done the third-year quantum mechanics course here. We're hearing more and more these days that teaching is core to universities. most of what we do as research is teaching. When we're working with PhD students, we're teaching PhD students how to do research. We're certainly doing outreach when we present to other people, to our colleagues. Is teaching just presenting knowledge? That's often the way it's done. Here is my knowledge, absorb it. That's not what it should be. I think the key to being a good teacher is to actually understand what students know. And this is where we're seeing things like peer instruction and active learning emerging. So it's often said that if a student can explain to another student a concept that the lecturer has just presented, that will be much better than if a student tries to listen to just the lecturer. Because if you're a third-year undergraduate, you know what you don't know. Whereas if I'm a physics lecturer or professor or whatever I am, I've forgotten all of the steps I had to go through to understand third-year quantum mechanics or first-year classical mechanics. And that's where I think you have to build bridges. You have to try and go back in your mind and think about what you didn't understand as an undergraduate in order to teach well. You need to use other students to do that. You have to bridge that divide. Something I've been doing recently is using IPython notebooks to try and build intuition. So you can see here, there's a little excerpt of it on the screen. And my first year waves course that I've just recently stopped teaching, I turned all of the lecture notes into IPython notebooks where every single figure was interactive. So as a student, you can go in and you can change the damping factor on a harmonic oscillator and watch what happens to the graphs. And I think that by doing that both with classical mechanics and quantum mechanics and thermodynamics and solid state, then with the simulations you can actually get a much more vivid understanding of the physics that you're looking at. Culturally, you have to work hard. So my biggest experience of living in another culture was living in Japan for a year. So I went to the International Center for Young Scientists at the National Institute for Material Science for a year from 2004 to 2005. They described it as a melting pot. They wanted to bring together the arrogant, excited Western scientists along with maybe the more respectful and calmer Japanese scientists, and rub them together, try and make some sparks. This is actually that was how they described it in the promotional literature. And there are fascinating cultural clashes. It took me about 3 weeks to understand that when I asked one of the administrative staff if I could buy a particular computer from Texas, and they said, it might take a little time, that meant no. And I had to go through this several times. Sumimasen, chotto, if you know a little Japanese. I think that's the equivalent. I had to go through this 3 or 4 times before I twigged what was going on. And then I said, oh, could I buy it from this Japanese dealer? And the answer was, yes, of course. There was a reason for this in that the funding came directly from the Japanese government, and the Japanese government wanted to use Japanese companies, which is perfectly reasonable. But just understanding the idiom was very difficult. It's not a universal thing, but certainly there is a tendency amongst Western scientists to rush headlong into something that's going to fail catastrophically, or possibly succeed. And amongst Japanese or possibly other culture scientists to be a little bit more cautious and step-by-step and risk-averse. This was one of the things that the ICYS directors said they wanted to try and break or change. There's also the question of respect. There were a number of situations when the Western postdocs were very frustrated with the Japanese rules and showed no respect at all for the culture they'd come into, and it caused enormous problems. Again, if you're willing to build bridges, spend some time and understand the culture, I think you will get better. And for me, it was a fascinating experience becoming functionally illiterate. I could not read. You would go into the supermarket, and unless you knew exactly what to buy, you were stuck. And for me, that was eye-opening. You know, it really transformed my understanding of what it is to move to a different culture, and what a privilege it is to be able to read and to be highly respected, to be highly educated. The final thing I want to talk about in terms of building bridges is to do with faith in science. I'm not going to talk long about this, and I'm certainly not going to proselytize. But as a Christian, for me, it's important to say that faith and science are complementary. They do not contradict each other. We see many, many headlines about evolution versus creationism. You have the evils of the American Creationist Institute trying to prove that dinosaurs walked the earth at the same time as humans. As with all media stories, this is a massive exaggeration. You have many, many scientists who are people of faith. You have many churches which are very open to the idea of evolution. Faith is rational. science involves belief. Or possibly, if you want to choose other ontological or teleological terms, you can. But I think that that is certainly safe to say. And I think it's important that we understand that. I've often encountered this kind of underlying assumption in the hard sciences that anything that is not immediately in front of you in the real world that can be hit with a hammer is not worthy of attention. And I think that's not fair, neither to faith, nor to philosophy, to the arts, or to various other areas. I wanted to say that that's important to me. Where next? What am I going to do next? Mike is going to laugh at this. We are going to release the CONQUEST code. We have been saying we'll release the CONQUEST code for a number of years now. But we will be releasing it in the next year or so. That is my firm hope, my firm intention. We want to apply CONQUEST to many different problems, to biomolecules and related problems. You can see up there again the F1 ATPase. I would love to be able to do a calculation on a system the size of the STM image you can see on the bottom right. 10, 15, 20 nanometers, dopants, charging, the electrostatic effects of a tip. And I think there are reasons to believe we can do that with CONQUEST with ab initio accuracy. It'll take some time, but I think that's possible. Something I'm getting very interested in is oxides and ferroelectrics and large-scale features in oxides. I will, of course, continue interacting with experiment, and I want to explore further this idea of how simulation can work in teaching, how we can use the power of computers to give people a much better intuitive understanding of the physical world. So with that, let me finish. I hope you've seen that, to me at least, experiment and theory are a vital collaborative tool. Linear scaling DFT is promising. It's very difficult to persuade the wider community of this because we've got very good at doing n-cubed standard DFT calculations with a few hundred atoms. So we have some work to do, and bridge building is key. There are a couple of references there to review articles I've written, one on nanolines, one on CONQUEST, and associated linear scaling methods. There is a book there, which I wrote with Veronica, and there are some websites. So Atomistic Simulations is devoted to the book, and I blog there from time to time. Order N is CONQUEST, and if you're interested, you can follow me as Million Atom Man on Twitter. Thank you.